which is the most famous, and also for some other category. And here we will try to get an analogous version of this theorem for Kuntz semigroup. So first, let me remind a bit how an approximate intertwining is working. So given two sequences of C-star algebras, okay, so we know that they have both. They have a limit in the category of C-star algebra, and so maybe those two inductive systems, they don't really look the same. The morphisms are different, the algebra are different, but still we want to know if those algebra in the limit are isomorphic or not. And a way to do this, to prove this, is to study morphism at finite stage. So the main point is trying to find star homomorphism that goes back and forth from the top sequence to the low sequence, like this, that makes triangles. And instead of, so obviously if we have commutative diagrams, it's really easy to prove that the inductive limits that we have are isomorphic. But the approximate intertwining technique allows you to get a weaker assumption and still get an isomorphism in the limit. So what you want to have is approximately commutative triangles. So the upper and lower triangles need to approximately commute, in the sense that for some finite set that will get bigger and bigger at each step of the sequence, going this way, so up, down, and up again, or straight, gives you the same elements up to a distance, up to an epsilon. And this epsilon needs to goes down to zero quick enough, and the sets on which the triangle commutes needs to be big enough at each steps to be able to conclude a star isomorphism. So I will not enter into technical details, and I hope and guess that most of you are familiar with this approximate intertwining technique. Let me also mention what are the use of such a technique. So there are, over the past decades, there were many use of this kind of technique. So one of the first would be the classification. Let me write big. Classification of AF approximately finitely algebra. So those are inductive limits of finite dimensional C-star algebras by means of their K0 group. So this was done by Elliott in 1976. They also, the approximate intertwining also play a key role in what I will call classification machinery. So this is a technique that has been widely used to obtain theorem of classification of C-star algebra. So the point is to find a functor. So maybe let's write it here. The point is to find a functor F from the C-star category into an abstract category that will what is called classify star homomorphism up to a certain equivalence class, meaning that for any morphism of the codomain category, we can find a lift, a star homomorphism that such that f of the star homomorphism will give you the morphism in the abstract category, and this lift is unique up to a certain equivalence relation, which is the approximate unitary equivalence relation. And using the approximate intertwining technique, we can conclude if a functor is classifying star homomorphism of a certain category of C-star algebra, that it's a complete invariant, which is a quite strong tool. And lastly, these approximate intertwinings were used in the construction of the Jiang-Su algebra, the original construction. So by Zhang and Su, 99, okay? So we see that there are a lot of application to this kind of techniques, and especially in the classification of C-star algebra. And now we will see a bit about the Kuntz semigroup, and we will end up trying to apply this kind of argument in the Kuntz category, okay? So on the other hand, we have so the Kuntz semigroup. This subject has been kind of a valuable assets in regarding the classification of non-simple C-star algebra, because it's a rather complex subject, but it captures really well the structure of the ideas of the algebra. And but unfortunately, for one part, it's really hard to compute, and it's only since 10 or 20 years that it arises as indeed a good invariant for classification of C-star algebra. So the Kuntz semigroup is a useful tool regarding classification of non-simple C-star algebra. Let me give you some examples. So the most notable one is the classification of non-commutative CW complexes done by Leonel Robert in 2012. So he showed that, so I will write Cu to mean the Kuntz semigroup. So the functor, which is actually a functor from the C-star category into an abstract category that I will describe next. So the functor Cu classifies star homomorphism from any inductive limit of non-commutative CW1 complexes of dimension 1, which I will write MCCW1 to any C-star algebra of stable rank 1. Okay. So this is the classification machinery that I was talking about, and a corollary of this theorem is that a fortiori the Kuntz semigroup is a complete invariant for any inductive limit of non-commutative CW complexes. I will describe exactly what are those, but to give you an idea, this is a rather large class of C-star algebra within the class of stable rank 1 C-star algebra. Okay, so you have, I forgot, we need a trivial K1 hypothesis. Okay, so this is just the introduction, I will specify why. But for those who are not familiar with those concepts, so the Kuntz semigroup is an object that captures really well, so as I said before, the structure of the ideals. But as far as elements are concerned, it's based on positive elements. So you have the traces and the K0 information to sum it up, but you don't have K1 information. So this classification, for example, will be limited to the trivial K1 hypothesis. Okay. So this is a really nice theorem, but for instance, since the Kuntz semigroup is really hard to compute, in practical, if I construct two C-star algebra as an inductive limit of this class of system algebra. I might not have the right tool to compute it, and I might not be able to know if the Kuntz semigroup of those inductive limits is isomorphic or not. So this is, for example, one of the use that we might try and get some approximate intertwining techniques for the category CU, so that we can really apply concretely this kind of theorem. Okay. So I know most of you might not be familiar with the Kuntz semigroup, especially. So I will first make some preliminaries about this invariant, and then we will enter in the approximate intertwining techniques for the category C. Okay. So let me first define. So I will not get into the CU semigroup of system algebra per se. I will work with abstract Kuntz semigroup. So I will define those, and I will still recall what is the Kuntz semigroup of the system algebra, but this is not the main point of the talk. Okay. So first we need a definition of what will be called an auxiliary relation. So let me start with partially ordered set that I write post set. Okay, so it's just a set with a partial order. And let me take two elements in this set. We say that x is way below y, and we denote it with this double sign. Okay, I hope you can see. Okay, we say that x is way below or compactly contained within y if for any increasing sequence of my post set that has a supremum, and this supremum is bigger than the biggest element, then there is a finite stage of the sequence which gets bigger than the smallest one. So meaning there exists so let me write the sequence for any increasing sequence Sn. So there exists some n such that Sn is bigger than x. Okay, so this is kind of abstract notion, but this is really important for the Kuntz semigroup because this is what will allow us to get topological property. Okay, so the way below relation, or else called compact containment relation, allows us to get the topology. So it's an order theoretical topology for CU semigroups. Okay, and let me give you some example. So if X is a topological space, and I consider S to be the open set, and I give it the structure of the inclusion. Okay, so an open set is way below or compactly contained within another. This exactly means that we can put a compact set between the two open sets. Okay, to give you an idea of what is this compact containment relation. Okay, another example. So the most basic one, if I take the natural number with the usual order, a natural number is way below another one, so n is way below m, this exactly means that n can compare with m, okay? And I get the opportunity of this example to give you the definition of what is a compact element. So when x is way below itself, we call this element a compact element, okay? So now that we have this definition of the way below relation, we're able to define and describe the Kuntz category, okay? So if you have trouble to read, let me know and I will try to write bigger. So the category CU. So CU goes for Kuntz, obviously, Kuntz. So let me describe the objects first. So the objects of the Kuntz category are positively ordered monoid. So let S be a positively ordered monoid. That I will write POM, okay? So S belongs to the category CU if it satisfies the following axioms. There are four. The first one is kind of an analogous of completeness. So I will describe this later, but knowing that we have a topology that will be based on the way below relation. So it says that any increasing sequence has a supremum. Okay. The second one is that any element can be approximated by an increasing sequence, but for the auxiliary relation, is there a question?
I think someone was just mistakenly unmuted.
Okay. Don't hesitate if you have questions, of course. So any element can be approximated by a compactly increasing sequence, meaning there is a sequence which each term is way below the next one, and the supremum of this sequence. So obviously, if you are compactly contained within Y, you compare for the other to Y. So a fortiori, this is a star increasing sequence which has a supremum, and any element of the monoid can be written this way, can be approached by such a sequence. And O3 and O4 are compatible axiom, okay, between the operation that we have and the compact containment and the operation and the suprema. Okay. CU morphism will just be POM morphism, positively ordered monoid morphism, that respects the compact containment relation and the suprema of increasing sequence. Okay. So as I stated, the way to have a topology and this kind of algebraic object, because they are monoids, is to use the compact containment relation, which gives you another theoretic topology. So the topology is called the Scott topology. So I might not enter too much in detail with this, but basically you can picture the open sets. So as a topology. So it's called the Scott topology. Okay, and the other set, so another set will be of the form, the open sets are, so if I take an element, I can write, this way, okay, meaning all the elements of my CU semigroup that are way above the element S, okay, meaning S is way below all of those. So this is an open set for the Scott topology, and this generates a topology on S. And this is what we're going to use to build our approximate intertwining. Okay. Let me briefly recall, but as I stated before, this is not the main point of the talk. But for a C-star algebra A, the Kuhn semigroup of A is defined as classes of positive elements under a certain equivalence relation, which is called the Kuhn's equivalence relation. Okay, so for those who have never seen this construction, you can picture it as extension of the Murray-Van-Neumann monoids. So that takes projection, make classes of projections, but you just extend it to positive elements, so you get wider objects. Okay, and finally to give you some example of abstract Kuhn semigroups, and that we will use actually in the future. So this is one or several theorems from Antoine Pereira and Santiago in 2011. So they show that under some hypothesis on X, which is a topological space, so let X be, so it has, for example, to be compact, Hausdorff or metric topological space of finite dimension as well. Okay, and S being a Kuhn semigroup, we can construct a wider Kuhn semigroup, which is construct as what is called lower semi-continuous function. Okay, so from X to S, and lower semi-continuous function are just maps from X to S. Okay, but are continuous. In which sense? In the sense of the Scott topology. Okay, so here I defined the Scott topology earlier, and X is a topological space, so this makes sense to talk about continuous function. Okay, so we say F is Scott continuous, and this provides a lot of example of abstract Kuhn semigroup. And the other part of the theorem states that under some circumstances, some hypothesis, let's say on X, which more or less matches those one, and for some, not any system algebra, but some restriction on the algebra, we have that the Kuhn semigroup of the tensor product of the continuous function over X tensor with A, when you can say that A is AF algebra, for example, to not go wild. This is isomorphic to the lower semi-continuous space from X that takes value into the Kuhn semigroup of A. Okay, so we will deal mostly with this kind of abstract Kuhn semigroup. Okay, so now that we have recalled a bit about those abstract Kuhn semigroup, we want to construct approximate intertwinings. So if we want to copy what was done for sister algebra, we see that there is a lot of topological arguments. For example, so you need a metric, you need to be able to compare morphism using distances. You need to be able to construct Cauchy sequences, use the completeness of the sister algebra. So here it's a bit more, at least less obvious, because the topology that we have is order theoretic. So first of all, we need to be able to compare morphism. Okay, so we define the first way to compare morphism in the most abstract way. So if I have two CU semigroup and a CU morphism between them, okay, we say that I need two morphisms because I want to compare them, sorry. So I take two CU morphism that has same domain and codomain, okay? And we say that they compare that alpha. So this is compare, and respectively, we define a strict comparison. So alpha compares to beta, or alpha strictly compares to beta on some set. So lambda is a subset of the domain, okay? And here we have to use the order theoretic topology that we have. So the only natural way to do it is that for any pair of elements that are in my set, which I want to compare my morphism, okay? For any element, on any pair of elements in lambda, such that one is way below the other, I will ask that both images of the smallest element are either smaller, or if I ask for strict comparison, are way below both images of the biggest element. Okay. So you can see that, for example, if lambda is my whole domain, if lambda is equal to S, and that they compare, since I can write any element of the Kuntz semigroup using the axiom that I had as the supremum of way below increasing sequence, I will get that any element of S going through alpha and beta has the same images. So a fortiori the alpha equal to beta, okay? So remark, if alpha compared to beta, and I don't even have to compare it on the whole semigroup, I can just compare it to what is called a dense subset, which means it's a subset that any element can be written as a way below increasing sequence of element of the subset. So that's why S is a dense subset of S, obviously. And we have a natural dense subset, which is all the elements that are way below someone. Okay, so this is also a dense subset. So if the two morphisms compare on this natural dense subset or another one which is even smaller, I can conclude using the Kuntz axiom that the morphisms are the same. Okay. And in practical case, so we don't want this lambda to be huge. We actually want it to be finitely generated or finite. And that's why I need to be able to approach any element of my Kuntz semigroup in a uniform way, like a controlled way where I know where the approximation of my elements will end up on some lambda that I choose beforehand, that has some nice property. Okay, so this follows me into defining what is a topologically based Kuntz semigroup. Let me state that this name might not be the most accurate one, most adequate one, so it might change in the future. But for the rest of the talk, this will have this name. So if I have a Kuntz semigroup, so as I said, I want to be able to not only approximate any element of my Kuntz semigroup by a way below increasing sequence. I want to be able to approximate it with someone that is way below, but I know where does this way below lives, and all the way below lives in the same place. So let me be a bit more clear on this. So if I have
before you go to the next question, I wanna ask you a question about the previous definition. So could you please interpret this definition if you take CU of closed interval 0 and 1 and say what the interpretation of the last statement is?
this one.
Yeah.
Yeah, okay. So the intuitive way to see it is that if you take lambda to be, for example, the whole semigroup or a dense subset, okay? So if I have, let's say lambda is the whole semigroup, okay? So this means that for any two elements of my semigroup, such that one is way below the other, okay? So for now, let's forget about the strict comparison. Let's just go with this one. I can say that the images of the smallest one of both morphism compare with the images of the biggest one, okay? And now if you want to conclude that alpha is equal to beta, the way to do it is with the axiom O2 that satisfies any Kuntz semigroup. Any element of my, I just write here. Any element of my domain, I can write it as the suprema of a way below increasing sequence, okay?
Yeah.
So for any k, I have that sk is way below sk plus 1, okay? So now I put this within this machinery that I have. So what this tells me, it means that alpha sk, okay, will be smaller than beta sk plus 1, okay? And now if I go to suprema, for example, to the right first and to the left first, this obviously this is, so I told you that Kuntz morphism were a fortiori monoid morphism, okay, that reflects suprema. So I know that beta of sk plus 1 is smaller than beta of s, okay? And now I go to suprema because alpha is a Kuntz morphism. I can say that alpha of s is smaller than beta of s, okay?
Oh, I see.
And now the argument works the other way around, and I can conclude that alpha of s is equal to beta of s for any element because I can use these O2 axioms. And this is why you can see that you don't even need to have that they compare on the whole semigroup. What I call a dense subset is a subset lambda that any element of S can be written as the supremum of some element of lambda, okay? So this is the definition of the dense subset. So now the point really will be to be able to, knowing that we have a dense subset that might be countable, for example, to somehow discretize this dense subset into submonoids that goes bigger and bigger, and to know at which stage the comparison stops. And if the comparison doesn't stop, then this means that the distance is 0. And if it stops at some stage n, let's say, so the distance is 1 over n, and we will be able to know how close two sigmomorphisms are one from another with kind of a discrete metric. Okay, so this is the intuition that is behind the idea. And thank you for the question, because it helps me to explain the next definition.
Thank you.
Okay. So now that we have this, so as I stated, this is always a dense subset. So this is the set of elements of S that are way below someone. Okay, that means there are not like infinite elements, for example. So if I have a Kuntz semigroup, I say that S is topologically based. So the name might change in the future, but anyway, if I can find a family, so a countable family of pairs, so this I will call B. So it's a countable family of pairs where the first component is a positively ordered monoid, okay, and the second component is a polymorphism going from the dense subset of the elements that are way below someone to the nth positively ordered monoid, and it has to satisfy the following. So the first point is that the MNs are an increasing sequence for the inclusion, okay, within this dense subset of my Kuntz semigroup. And the second fact is that this sequence of epsilon n s has to be an increasing sequence, or the order has to be an increasing sequence in this subset, which is the people that are way below S, okay? And the supremum of this sequence is S, okay? So to give you an idea, this means that for any element S, that is, so for any element S of my semigroup, I can construct a sequence of people that are way below, okay, and it's an increasing sequence of people that are way below my element that I want to approximate by way below way below elements, okay, and I know exactly where do they end up at each step of my sequence, okay, and where they end up is as a nice structure of positively ordered monoid that later I can use to define my distance, my metric to compare morphisms. Okay, so some remarks. So if I have this, the union of all the POMs, okay, which is a increasing sequence of POM, the union will be also a dense subset because I can approximate any element with a sequence that is of the form epsilon n of S. Okay, so this is the first remark. A second remark is that some example that any finite sum of natural number with the infinite, so this means the natural number with the infinite, so this is the canonical Kuntz semigroup, let's say. So any finite direct sum of those are topologically based, okay? And this definition allows me to get, if not a metric, a semi-metric on CU morphism, okay? So for any alpha, beta that are CU morphism from S to T and S is topologically based, I can define so this will depend on the basis that we have, the basis of topology. So it's, as I explained earlier, it is the infimum of 1 over n, such that alpha compare with beta on the set Mn, okay? So we want to know how far, how close we can get to any element so that the two images with the morphism compare, and if it's for all the Mn, we get to the reasoning that I get earlier, and we get that the two morphisms are equal, okay? So if they compare on Mn, we say that, and not on Mn plus 1, we say that the distance is 1 over n, okay? So this gives you a semi-metric. Just a small remark that this depends on the basis that we choose. And in the practical case we'll be working on, which is lower semi-continuous functions, all those semi-metric for any base that we can construct will be equivalent. So we will not be really worried about this, okay? So maybe let me speed it up a bit. So let's go to approximate intertwinings. Okay. So the proof will be, the hypothesis will be more or less the same, just adapted to the setting we are in. So basically the theorem states, if I have two inductive sequence of topologically based Kuntz semigroup, so S1, T1, and Tn plus 1. So now that I'm able to kind of compare morphism, I want to know if I can find some analogous argument to say that comparing the finite states, if I can deduce the CU isomorphism between the two limits. And the hypothesis will resemble a lot of what we had for C-star algebras. So I have to find CU morphisms, okay, such that, so now I have to find what does it mean to approximately commutes, okay? But now that I can compare morphism, let's say that, so I will not write down all hypotheses because maybe I will not have time to finish. But let's say that you ask for each of the upper and lower triangle, okay, to commute on poems that are part of your base that are bigger and bigger, okay? So you ask for the, equivalently, you ask for the distance between this path and the straight morphism, and the same for the lower triangle, to go down to 0 fast enough, okay? And then you are able to use all these kind of technical tools to get CU isomorphism between the two, okay? So the main point was really to construct, if not a metric, a semi-metric, to be able to get this the same. The argumentation is not the same. The proof works really differently. For example, we don't use Cauchy sequences because we don't have this kind of object. But it will work the same way. So the proof is really technical. and it's quite long, but let me just sketch you a bit. So basically what will happen is that I start from some SI, no? And I have an element S in SI, and I stated that I can approximate this element in a uniform control way with those epsilon n morphism, okay? So basically I have the nth approximation, which is way below the mth approximation, which is way below my elements. And I know that the further I go, okay, the smallest the distances between my triangle is, okay? And so the idea will be to go away far enough, okay, so that I can send the so I can send the smallest approximation in here, and the biggest one here too, and they will also be, they have the same comparison because we work with C-homomorphism. So when I look at them in another semigroup of the sequence, they still are, the smallest is way below the biggest. And now using the fact that I can go far away enough so that they compare on almost all the MNs because the distance goes down to 0 fast enough. So basically, then the smallest one will go down this pass, while the biggest one will go down the upper pass, okay? And because the triangle compares, this tells me that the images going down this pass of the smallest one is smaller than the images go down to the biggest pass, okay? And then I send everyone to the limit that is T, okay? And what do I get is that I get an increasing sequence. So it has a supremum, and basically like this, I can construct a morphism from SI to T, okay? And this I can do for any SI, and plus those morphism respect the universal property, which gives me a C-homomorphism from S to T. And I do the same kind of argumentation from the lower sequence to the upper, and I get another C-homomorphism from T to S, and then I can show that they are inverses of one another. Okay, so this is kind of technical, so I don't want to spend too much time on this. But you can see that the way of proceeding is the same as before, even though the argumentation is quite different. Okay. Yeah, let me go to the next section. So this is all very abstract, and now I wanted to give you some example. So of topologically based Kuntz semigroup and some application of this kind of techniques. So first, to be able to compare morphism, to be able to compare Kuntz morphism, and this approximate intertwining technique. So, okay, let me speed it up a bit. So, example of topologically based Kuntz semigroup. So as I told you, any finite sum of natural number with the infinite will be topologically based, and this class of abstract Kuntz semigroup corresponds exactly to the Kuntz semigroup of finite dimensional system algebra. Okay. We also have the lower semi-continuous function over some x that I will specify into those finite direct sum, and x is a graph. Okay, so a compact graph. Okay, so a compact graph can be seen as a CW complex of dimension 1, which is finite. Okay, so this corresponds in the concrete case to Kuntz semigroup of continuous function over this graph tensor some finite dimensional system algebra. And lastly, we have the Kuntz semigroup that can be written as pullbacks of the first two ones. Okay, so if I construct the pullback, one of those, but X is the interval. Okay, and I kind of do the same construction that is done for the circle. So I just forced the evaluation on 0 and 1 to satisfy some condition. Okay. So, okay, I don't want to enter too much in detail, but this can be done in the Kuntz category. These pullbacks has sense. And those are exactly the Kuntz semigroup of non-commutative CW1 complexes. Okay, that I mentioned in the beginning of the talk, which is a rather Laplace of stable rank 1 system algebra, which is the main study of my research. And those are topologically based too. Okay, so before quickly show you some application of all of this, let me just, not too much in detail, but show you, for example, how we construct a base of lower semi-continuous function over the interval. Okay, so the way to do it, so we have okay, a lower semi-continuous function on the interval to the natural number with the infinity will resemble to something like this. Okay. So you always have the point of continuity that is on the low part of the discontinuity. Okay. And what you want to do basically is to discretize your space, okay, which is the interval of a regular of an equidistant partition of size 1/2 of n, okay. And here, what you will do is that the monoids mn's are the lower semi-continuous function that are constants on each of those open sets. Okay, so each of the open set of the partition. So we can see that if we go to mn plus 1, we get a monoid that contains the previous one because it's just getting a finer partition of this. And the way to approach any map that is lower semi-continuous over the interval is just to get the biggest element that lives in Mn. So that means that is constant on any open set of the partition that is way below the element that we consider. So for example, here, I can see that this point of the partition is already out of the support of the function. And so here, let me take another color. Here I will have to take all of those, okay? And so this lives in Mn, and when I go to Mn plus 1, my partition is finer. So I will slowly get another element which is in between my element that I want to approximate and the approximation that I already had. And I get a finer, way below approximation of my element. And I can show that going n to infinity, that I recover my element that I was approximating. And this is a basis of topology. And I can have a metric there. And yeah, I don't have so much time left to explain, but the main idea is this, okay? And I can mimic this kind of discretization of the topological space for any graph. So for example, for the circle, it will work for any graph, and I can extend those results to Kuntz semigroup of non-commutative CW complexes, okay? So quickly, some applications of this. So let me mention that for the circle and the interval, those special cases, Kuntz distances have already been defined, and they will be equivalent to the discrete metric that I defined here. But the processing of this discrete metric allows me to not restrict myself to the concrete case of the circle of the interval, okay? And I get an equivalent metric. And for example, the first application that I can tell you is that the Kuntz semigroup, so the functor Cu, classifies unitary elements of any AF algebra, okay? So the way to do this, and then I will stop. So the way to do this is to see unitary elements as a star homomorphism from the continuous. So let A be, for example, for starters, a finite dimension C-star algebra. So the unitary element of A, so let's say it's unital, if not, you can unitize it. You can see it as star homomorphism from the continuous function over the circle to my algebra A, okay? And basically, so the proof is stating that the Kuntz semigroup classify homomorphism from the continuous over the circle into an approximately finite dimensional C-star algebra, okay? And the way to do this is to use the discrete semi-metric that I have, not on this, but now if I pass this into Cu, okay, I get home Cu, and now the Cu semigroup of the circle is the lowest semi-continuous over the circle into N, okay, and the Cu semigroup of A, which will be a direct sum of natural numbers. Okay, let me just finish this and then I stop. So a unitary of a finite dimensional C-star algebra, you can see it as a bunch of points that lives in the circle, okay? And the image of an indicator maps of an open set of the circle, okay? What will it do? So when I consider my unitary element as a morphism, it's just counting how many points of my unitary is there in this open set. And now that I discretize my circle into 1/2n partition, I can just look at the images of each of those to recover and construct a lift that is my unitary. So yeah, sorry, I don't have much time to enter this detail, but it's a nice application. And let just me end up with saying that the main application of the approximate intertwining theorem is to compute when we have inductive limits of C-star algebra to get this inductive system into the Cu functor and to measure the morphism at each step and to know if we can find an approximate intertwining theorem to know if the Kuntz semigroup are isomorphic. And this, I use it in one of my example of my thesis where I construct two C-star algebra that has some required property and I can show that their Kuntz semigroup is isomorphic. Okay, so I will stop here. Sorry for speed up a bit at the end. And That's it. If you have any question.
Okay, so do we have any questions?
There's
I
a
mean,
nice
understand.
echo in the room. Yeah.
Sorry, what?
I'm sorry because it sounds funny when you are talking in the tea room.
That's because two of us had our microphone and sound on, and there was some feedback. Sorry about that. Right, so any questions other than why I sound like I'm in outer space?
So is it the most general version, the last theorem that you already mentioned, is it the most general version of your theorem? Namely, I mean that can you develop AF algebra to some, I don't know, maybe AT or
This it's actually a good question. So this is not the main theorem of the paper. This is like an application that I actually did a bit before, but we cannot extend this to AT or AI algebras, and we were able to construct actually an example of two unitaries that lives in an NI algebra. And this AI algebra is actually one of the most basic one. So it's the continuous function over the interval tensor m to infinity. Okay, and so this thing. So basically, this tells you that for any morphism from the Kuntz semigroup of the continuous over the interval into the Kuntz semigroup of an IF algebra, I can find a star homomorphism, which is a lift, and it's unique up to approximately unitary equivalence. Okay, and this is doable because when you represent your unitary element as points on the circle, so finitely many if it's unitary of finite dimension, or infinitely many if it's AF algebra, those points, don't move. Okay, and as soon as you go there, okay, so you can construct the first unitary that has infinitely many points. So the way to construct in M to infinity, for example, is actually the explicit unitary that we have is so you know that this one is constructed at inductive sequence of M2 power to n. Okay, so at the finite stage, my unitary will take all the equidistance points of 1/2n in the circle. So this is a unitary, and I go on filling the circle like this. So at each step, I add more points that are in the finer equidistant partition of the circle. So I get a first unitary, and I tensor it with the function that is constant over the whole interval. Okay, so I will get a unitary that all the points don't move, and the spectrum of my unitary is the whole circle. Okay, and now I construct the same unitary in my AF algebra, but I tensor it with the identity. So what I will get that all my points over the time, which is 0 to 1, make one rotation. Okay, so the point 1, for example, within the time of between 0 and 1 will go like this. Okay, and as I explained, at least I try to explain at the end, the Kuntz semigroup, the Kuntz morphism that goes from the Kuntz semigroup of the circle into my algebra, which is an identification of my unitary, is just capturing how many points do I have within an open set, which correspond to an ideal of the circle. Okay, and if you can see this, the movement that it has every time that one point goes out, one point comes in. At level of Kuntz semigroup, you don't see this information. So the first one where the points, they don't move, so you always have, let's say, between one ideal and one that is slightly bigger, which is compactly contained in the smallest one. Okay, so you will have a certain number of points and another one that you can compare. And for the unitary that is moving, you will not see any difference. And the distance between those two, so it's not between the two unitaries, but between the two CU morphism that represents your unitary will be 0. Okay, and so the information that you need to be able to distinguish those unitaries, because they are not approximately unitary equivalent, is to add some K1 information. So this is part of the whole other article that I'm writing, is how to extend, how to add K1 information within the Kuntz semigroup. So on the one hand, to solve this kind of issue, and for example, to at a larger scale, to maybe extend the classification result that we have, that most of the time impose trivial K1 hypothesis. And so this would be a way to just generalize these things. Okay.
Thank you.
Any other questions for Laurent? If not, let's.
Well, sorry, I wanted to say that, yes, this intertwining argument, yeah, this is typical in modern Fraser theory. So perhaps it can be generalized to some categories which are enriched over metrics or quasi-metrics, maybe, yeah. So yeah, it seems that there is something that could be made more general than what you are saying. But I mean, I like your lecture in general. Yes, it's only this what I understood, this intertwining argument. Yeah, but
Yeah.
since it plays some crucial role, then why not to develop it further? Yeah.
Okay, so you have to. There is already some work that is done when you have.
Well, there is this something called Fraser theory, or theory of universal homogeneous structures, and there is approximate variant of it, also developed by some people in C-star algebra, like Martino Lupini, Jordi Lopez Abad, perhaps.
Okay.
By the way, since you are in CRM, it is in Beaterra, right?
Mm-hmm.
Yes, so maybe you know Jordi Lopez Abad. He's not in C-star algebra really, but he's close to it. He's
Okay.
in Madrid, after all.
Yeah, so it's next door, but not really.
And yeah, I wanted to say that, but it is just a very informal comment. I spent some time in Beaterra in CRM, and it was really fantastic. It's a beautiful campus.
Okay.
So I somehow envy you that you are here, that you are there.
I will be most likely leaving at the end of the year, but yeah.
Yeah, well, I spent there just several weeks, and it was really, really very nice. Especially this time of the year, yeah, because it was like May, June.
Yeah, this is the nice time actually.
Yeah. Okay, thank you.
Okay, so I guess if there are no further questions, we can thank Laurent again. And if I can just share my screen to announce next week's talk. Give me a moment. Okay, so next week we will have Mike Whitaker from the University of Glasgow speaking, and he will talk about K-theoretic duality of self-similar actions. So I hope you'll be able to join us for that talk, same time, same place next week. And so see some of you then. Bye. I want to say hello to Ali.
Okay, bye-bye. Thank you.
Thanks. So Ali, how's the stuff in your new home upstairs?
So, yeah, everything so high. So, and everything is good. Yeah, everything is good. So thank you. Yeah.
Good.
And tomorrow I'm going to pass my PCR test, and if everything goes well with the results, so I will be free. So to go everywhere.
Yeah, we'll be able to get out of prison.
Yeah, that's right.
Yeah. It's a shame because we're just down in the tea room, but yeah, you can't really join us, I guess. So, but
Yeah.
next week you'll be able to.
Sure.
All right.
There. Yeah. Okay. Thank you for asking. So,
Bye.
see you soon. Bye.